Hello everyone, and thanks for watching Edupedia World videos. In this video we'll start a new topic called capacitors. Capacitors are a device that is used in electronic circuits mainly to store energy. So the generic form of a capacitor would be two conductors of random shapes given equal and opposite charges. So if the first conductor is given a charge of plus Q, then the second conductor is given a charge of minus Q. Now if only these two systems exist and nothing else exists in the universe, then if I leave a positive charge here, then it's going to go towards the right because it's going to be repelled by the positive charge and attracted by the negative charge. Another way to say that would be the positive charge would have an electric field towards the right, the negative charge would have an electric field towards the right, and hence a positive charge left over here would move towards the right. That means to take a positive charge from this side to this side, I would have to do some work, which would be a manifestation of the fact that these two conductors would be at different potentials and there would be a potential difference between them. Remember, potential difference is nothing but the work needed to transfer a certain amount of charge from one point to another. Potential is the same thing but for unit charge. So let's say this particular conductor is at a potential of V plus and this conductor is at a potential of V minus. The potential of the negatively charged conductor has to be smaller because the positive charge goes from this side to this side, and we always know in mechanics that particles would like to go towards the negative potential energy region, as lower potential energy as possible. So the capacitance of this whole system is defined as Q by V. Now a couple of things are very important here and they are needed to be understood. The first thing is that Q is called the charge on the capacitor. Now this is a slightly misleading term because if this whole thing is the capacitor, then the total charge on the capacitor is actually zero, because one side of the capacitor, which is called the positively charged plate, this is similarly the negatively charged plate. So the total charge, or it would be the sum of the charges on the two plates, that would be plus Q plus minus Q, which would give me 0. So capacitors have a net charge of 0. The charge on the capacitor is the magnitude of either the positive or the negative charge on either one of the two plates. Right, so you need to remember this. In some advanced cases, you could have two different charges or different magnitudes on these two plates. We'll consider that at the end of this chapter. For now, whenever we are talking about a capacitor, if one plate has a positive charge of plus Q, then the other plate has to have a negative charge of minus Q, and Q will be called the charge on the capacitor. In my opinion, a better terminology for it would be charge on the positive plate, because that is what it is, but the terminology that is generally used is charge on the capacitor. So I want you to be careful about that. The total charge on this plate plus the charge on this plate is 0. So the total charge enclosed in this volume is 0. But the charge on the capacitor does not mean that. It means the charge on the positive plate or the magnitude of the charge on the negative plate. The second thing, V, is the potential difference between the two plates. What that means is it is equal to V plus minus V minus, positive minus negative. It is called the potential difference the two plates. So if we have two different conductors and we give one a positive charge plus Q and the other a negative charge minus Q, and we measure the potential difference between the two plates, that means we measure the work done in taking a unit charge from this point to this point. In that case, the ratio of Q by V is called the capacitance. The standard unit for capacitance is Faraday, which is the SI unit, but it is generally quite a large unit when you're dealing with everyday quantities. So a unit which you'll see very often is microfaraday, and that is nothing but 10 to the power minus 6 Faraday. Now, one of the ways we could give two plates of a capacitor equal and opposite positive and negative charges is by connecting the capacitor to a battery. Now we'll discuss batteries in much more detail in a later chapter, electricity, but right now there are very few things which you need to know about the battery to understand the following concepts. The most basic thing you need to know about the battery, it has something called an EMF. EMF is an electromotive force, but it's also a slightly misleading term as it's actually a potential difference. It is symbolized by E. And EMF is the potential difference across the ends of a battery when they are connected externally to something else. So whenever a circuit is completed in a battery, in this case the circuit is completed by using the capacitor, then the potential difference between the two ends of the battery will be E, or it will be V if V is the voltage of the battery. So EMF and voltage. Technically, there is a slight difference between the two things, and we'll deal with that in detail in current electricity. Right now, this is all you need to know, that every battery has a characteristic EMF, and that is the voltage difference between its two ends, the positive minus the negative. Very often, we'll take the negatively charged end to be at zero potential, then the positively charged end will be at a potential V. This is because you can choose the zero of potential or potential energy to be anywhere, and everything else is decided accordingly. Another thing you need to know about a battery is that it always gives an equal amount of positive and negative charge. If a Q amount of charge is flowing from this end, the positive end of the battery, to this plate, then a minus Q amount of charge must be flowing from the negative end of the battery to the plate. Or another way of saying that would be Q amount of charge is flowing into the battery. In other words, the charge inside the battery will always be constant. So if Q amount of charge is flowing out one end, then the same amount Q of charge must flow in through the other end. Right? So let's make this figure a little bit more clearly. These are my capacitors. Now at this moment, this is not a capacitor. At this moment, this is just two positively charged plates. They don't need to be plates, but more often than not, they will be plates. So two plates of a conductor which don't have any charge on them yet. And then what we do is we connect these two ends to a battery. This is the symbol for a battery. The longer edge represents the positive potential, the shorter edge represents the negative potential. And we know that the potential of the battery is V, or the EMF of the battery is E. In that case, if we assume this to be at potential 0, then this is at potential V. Since this is a conducting wire, a conductor is an equipotential, we saw that last time. So this plate also has a potential V, and this plate has a potential 0. Now if an amount Q of charge is flowing from the positive end of the battery, then an amount Q of charge must be flowing into the negative end of the battery. Where does this charge Q go? It goes at this end. And if this charge Q is coming into the battery, it must be coming from this plate. So if Q of charge is flowing out of this plate, then the charge on this plate is minus Q. And therefore we see that simply by attaching the two ends of a capacitor to a battery, we have created equal and opposite charges on the battery, on the capacitor. We already know V, we can measure Q, and C is equal to Q by V will give me the capacitance of this system. So this is the way capacitors are generally charged. They are attached to the batteries, and one end is attached to the positive end and the other end is attached to the negative end, and equal and opposite amounts of charges flow from the two ends of the batteries, and they end up resulting in equal and opposite charges on the plates of a capacitor, and the potential difference between the capacitor is V, which is the EMF of the battery. Now, an interesting thing about the capacitance is that it generally only depends on the geometry of how the plates are arranged. So we'll look at a couple of examples of different ways in which two plates can be arranged and calculate the capacitance in those particular cases. The first and simplest, and the case which you'll use most often, is what is called a parallel plate capacitor. Parallel plate capacitor, you have two sheets of conducting material kept a small distance apart. Now, what does it mean to say they're kept at a small distance apart? That means generally this distance is much smaller than this dimension of the sheet. So if this sheet is a rectangular sheet, then this distance D is much smaller than the length or width of the sheet. If this sheet is a circular sheet, then this D is much smaller than the diameter of the sheet. The reason we take that approximation is because we would assume that these plates are infinitely long plates, and we would use the formula of electric field which we use for an infinitely long plate. Remember, we said that if we calculate the electric field of an infinitely long plate and use it for a finite plate, it won't give an accurate answer near the edges, but if we are looking at a small distance and it is somewhere near the midpoint, in that case you can assume it to be an infinite plate and the answer will be approximately the same. So we will right now assume a parallel plate capacitor which has plates of area A, and we give them a charge Q and minus Q. So based on everything we've learned till now in electrostatics, all we need to do is calculate the potential difference between these two plates, and we would ultimately find out the capacitance. So the electric field in this direction from this plate would be, we've already calculated it previously, but I'll do it once again using Gauss law. We'll take a small Gaussian surface. Let's say both sides cylindrical surface have an area A dash. Then here the electric field is towards the right, here the electric field is towards the left. The curved surfaces will have no flux because the electric field is perpendicular to the area vector, that is, the electric field is parallel to the area. The flat surfaces will have fluxes, and this will have a flux E A dash, this will have a flux E A dash. So the net flux will be 2 E A dash, and that will be equal to the total charge divided by epsilon naught. Total charge here will be Q by A is the total charge into A dash is the charge within this area, and that by epsilon naught. A dash will cancel. Q by A, we can write it as sigma. Sigma is the surface charge density. So this plate has a surface charge density of sigma, this plate has a surface charge density of minus sigma, and from that we get that the electric field is sigma by 2 epsilon naught. So this is something we calculated previously. So the electric field of sigma by 2 epsilon naught exists because of this plate. Another electric field of sigma by 2 epsilon naught towards the right exists because of this negatively charged plate. The positively charged plate will always have a field away from itself. The negatively charged plate will have fields pointing towards itself. So the total electric field between this region is twice of sigma by 2 epsilon naught, that is E net. Let's say this is E plus. E due to the positively charged plate. E minus is also sigma by 2 epsilon naught, both are towards the right. So E net is equal to sigma by epsilon naught. Right? Now once you know E net is sigma by epsilon naught, you can calculate the potential, that is integral of E times dr. And the electric field is constant, the distance is constant. So what I can say is V plus minus V minus is equal to, using the formula, negative of integral of E dot dr, but in that case we are going from the negative plate to the positive plate according to the formula. If we are going from the positive plate to the negative plate, then we can remove the signs, and this will be from the plus to the minus. We remove the minus sign, and E dot dr will basically be E into d, because E is a constant, sigma by epsilon naught, and d is the total distance. So we get V is equal to E into d, that is sigma by epsilon naught into d, and Q is equal to sigma A. So from that we get the capacitance, that is Q by V is equal to sigma A by sigma D by epsilon naught, which is equal to A epsilon naught by D. And this is the formula which you'll definitely have to remember, because almost all of the capacitors we'll see in this course will be parallel plate capacitors. So the capacitance of a parallel plate capacitor is given as A epsilon naught by D. We see that this only depends on the geometrical quantities. A is the area of this plate, of both the plates, and D is the distance between the two plates, and epsilon naught is the standard constant of permittivity of free space. So this is the formula for the capacitance of a parallel plate capacitor. Let's look at another type of capacitor now, a spherical capacitor. In a spherical capacitor, we have two spherical shells which serve as the two conducting surfaces. So the first shell will be given a charge of, let's say, plus Q, then the second shell has to be given a charge of minus Q. Now all we need to do is calculate the potential difference between them, and the ratio of Q by the potential difference will be the capacitance. So what's the potential difference? For that we'll need to calculate the electric field, and we can integrate it. Right. By the way, this is called a spherical capacitor. So if we draw a Gaussian surface, I don't even need to do this. You already know the answer, but I'll do this. Gaussian surface at a radius r, we'll get E times 4 pi r square. We can use E into 4 pi r square instead of the flux, because we know the flux will be radially outward and only dependent on the radius. We saw everything like this in Gauss law. This will be equal to Q by epsilon naught. Q is the total charge enclosed, which is plus Q. So Q by epsilon naught. Minus Q will not contribute any electric field within this region. It will only contribute electric field outside it, because the electric field due to a uniformly charged spherical shell inside it is 0, which gives me E is equal to 1 by 4 pi epsilon naught Q by R square. Right. What I need is V plus minus V minus, that would be integral of, again, negative of integral of minus to plus, negative to positive plate, E dot dr. But since we are going from the positive to the negative plate, this is the direction of dr, this is also the direction of E. We can remove the minus sign and we can go from the positive plate to the negative plate, and it will simply be E dot dr, that is 1 by 4 pi epsilon naught Q by R square dr. The integral of this will give me Q by 4 pi epsilon naught times, this is R to the power minus 2, so integral will be R to the power minus 1 by minus 1. So 1 by minus, minus 1 by plus. That's what it will give me. So let's say this is the bigger one. This is R1 is the bigger one, let's say, and R2 is the smaller one. So what this will give me will be 1 divided by the positive one minus 1 divided by the negative one, because R to the power minus 2, the integral of that will give a minus sign. So it will be 1 divided by R2, that is the radius of the positive one, minus 1 divided by R1. What is this? This is V plus minus V minus, that is the potential difference. So we can see from here directly Q by V, we just have to take it to the other side. So Q by V, which is the capacitance, will be 4 pi epsilon naught R1 R2 by R1 minus R2. There. Again we see that it only depends on the geometrical quantities, in this case the radius of the two spherical shells. It doesn't depend on anything else. Finally, the third case and the least used case will be the case of a cylindrical capacitor. You know the electric field at a distance r away from a spherical shell, and you know the electric field at a distance r away from a cylinder. So you do the exact same thing. I'm not going to do it for you right now. I'm just going to write the answer, and I hope you can try it on your own. We know that the electric field for a cylinder goes as 1 by r. So E dot dr will incorporate a logarithmic element inside it. And you do the exact same thing you did in the spherical case. The steps are the same, the maths is the different. The final answer will be Q by V, which will come out to be 2 pi epsilon naught L by ln R2 by R1. So both the cylinders will have a length of L. The inner radius will be R1, the outer radius will be R2, and this will be the final capacitance. In the next lecture, we'll see how to deal with various combinations of capacitances, for example in series or in parallel. Thank you.